On October 26th, a sudden shift in the tracking data surrounding 3 Atlas was logged by multiple observation networks. At first, the anomaly appeared subtle, a handful of faint returns buried in the background of deep space scans. But when those returns were isolated and cross-referenced, a pattern emerged. They weren't noise, they were objects, massive ones. The initial telemetry suggests they've been trailing in the same orbital corridor as 3I Atlas for weeks, moving with a precision too exact to ignore. Their signatures are faint but consistent. No visible outgassing, no random dispersion, just quiet, deliberate motion through interplanetary space. This changes the timeline, it changes the risk models, and more than anything, it changes what scientists thought they were observing. For months, the focus has been on one object. Now it may be many. The official word is still silence, but the data isn't, and what it points to is far more complex than a lone interstellar visitor. The first confirmation came from a routine orbital model update. Analysts expected a familiar curve, a single track stretching towards solar perihelion, but the plot revealed a series of faint echoes flanking the primary object. At first glance, they looked like reflection artifacts or calibration noise, yet every independent telescope feed showed the same signatures at the same coordinates, moving with nearly identical velocity vectors. That consistency ruled out error. It wasn't background interference, it was structure. The echoes formed a loose envelope around 3 Atlas, positioned both ahead of and behind it along the same trajectory. The separations weren't random. Each object held a near-constant distance relative to the primary body, a spacing pattern rarely seen in naturally fragmenting comets. Fragment clouds disperse unevenly, but this was symmetrical, almost like a convoy holding formation. Teams monitoring the data describe it as a moving cluster, though no official term has been assigned. Estimates vary, but early models place at least 5 additional objects of significant size, possibly tens to hundreds of meters across. A few of them appear to be slightly brighter than the main body was at this same distance, suggesting either a reflective surface or a dense core. The timing of their emergence is critical. They appeared weeks before perihelion, just as solar glare begins to make detection more difficult. This isn't coincidence. It's a blind spot, a natural curtain in which movements are easy to hide. The cluster sits in an observation gap, a corridor of reduced visibility that will deepen as they approach solar conjunction. Astronomers now face a difficult problem. If these are fragments, their trajectories should diverge as sublimation accelerates near the Sun. If they remain locked together, it suggests something else. Either extremely stable internal structure or coordinated motion. That distinction will decide how the next weeks unfold. Radar and infrared scans show no outgassing jets or expanding coma around these objects. No tail, no visible interaction with solar wind. They're moving as if inert, but the brightest readings don't match inert rocks alone. Something in their composition or geometry is amplifying their signal without behaving like an ordinary comet. The discovery of these echoes is forcing mission planners to reconsider everything. The trajectory solutions built for a single mass are no longer valid. Each additional body modifies the gravitational environment in subtle but measurable ways. If the spacing remains constant, these objects could be functioning as a single system, something no one expected. When 3 Atlas first entered the record, and here's where the timeline sharpens, in less than 4 weeks, the entire formation slips behind the Sun. For nearly 2 months, ground-based telescopes won't have direct line of sight. Any changes during that period will go unseen. Whatever happens in that shadowed corridor will shape what we find when they re-emerge. The appearance of a cluster doesn't just add complexity, it rewrites the nature of the event. When analysts overlaid the new trajectories onto the original 3I Atlas path, something unsettling came into focus. The cluster wasn't drifting randomly through space. Each object traced a segment of a shared orbital geometry, repeating intervals, consistent spacing, mirrored velocities. Natural debris fields don't organize like this. Cometary fragments scatter along chaotic vectors influenced by solar heating, dust drag, and uneven sublimation. But here, the geometry held. The spacing between the leading and trailing echoes follows a near-perfect harmonic ratio, matching intervals observed across multiple days of tracking. No sudden acceleration, no spread, just quiet measured movement, as though each body is following an invisible template. That level of regularity isn't something a random breakup event typically produces. A subset of orbital dynamicists ran pattern recognition algorithms against known fragmentation models. None matched. The closest comparison came from artificial satellite formations in Earth orbit, where controlled spacing and synchronized movement are essential to maintaining formation flight. Of course, nothing about these objects suggests active propulsion, but the resemblance to controlled alignment is striking. Further analysis revealed a repeating orientation shift in their relative positions every 36 hours. It's subtle, a slow, synchronized rotation of the entire cluster around a shared axis. There's no known physical mechanism for comet fragments to rotate in formation like that. The pattern persists through multiple observation windows, indicating it isn't a data glitch. If it's natural, it's an anomaly unlike anything in current cometary literature. This is where the discussion inside observatories starts to fracture. Some researchers suggest the alignment could be a statistical fluke, a temporary illusion created by projection effects. Others argue the orbital plane is too stable for coincidence. It's the kind of regularity usually associated with engineered systems, not cosmic debris. What complicates matters further is the timing. The orientation shifts occur in phase with the object's forward motion, almost like a slow heartbeat pacing its trajectory. If this were a fragmenting comet, its pieces would drift outward, rotate independently, and eventually disperse. Instead, these objects pivot together like components of a single larger structure distributed along a path. The pattern is also spatially precise. When the formation is mapped in 3D, the objects align along a narrow cylindrical corridor stretching ahead of and behind 3I Atlas. The shape resembles a filament or spine, not a cloud. There's no wide arc, no trailing debris tail, no irregular fan. This alone has forced several research teams to reclassify their internal models from fragment swarm to structured cluster. A quiet alert circulated through certain research networks earlier this week. It didn't use sensational language. It simply stated, pattern stability observed, natural fragmentation models insufficient. No official press release followed. This isn't the kind of data governments or agencies rush to publicize. The implications go beyond geometry. A structured formation like this behaves differently under solar stress. If the alignment holds as the objects approach perihelion, they may survive in ways ordinary comets cannot. They may also maneuver or appear to maneuver in ways no passive body should. And behind the mathematics, a quiet question spreads through the analysis rooms. If it isn't natural fragmentation, what exactly are we watching? The shift in 3 Atlas's trajectory didn't happen all at once. It began with subtle deviations, fractions of a degree accumulating over consecutive nights. At first, analysts attributed these to thermal outgassing effects, the kind that push small comets slightly off their projected paths as they warm. But when the new cluster objects were factored in, the deviation matched something different, a gravitational nudge. The cluster isn't just moving with 3I Atlas, it's interacting with it. Each object, though faint on optical sensors, carries enough mass to create micro-perturbations in the trajectory of the primary body. These aren't theoretical models anymore. They're measurable shifts appearing in independent data sets from multiple observatories. When projected forward, those shifts compound, changing both the timing and angle of the perihelion passage. Gravitational resonance patterns between the objects appear almost too clean. In most natural fragment swarms, mass distribution is uneven, resulting in chaotic pull-push effects and unstable configurations. But here, the perturbations cancel each other out with eerie precision, keeping the cluster stable. It's as if their combined mass is tuned to hold formation without dispersing. This balance suggests more than shared origin. It suggests a kind of collective behavior, not conscious but dynamic. A configuration that's resilient under solar stress and gravitational drag. Some researchers quietly call it a locked array. If the objects are naturally formed, their mass and distance relationships are unusually exact. If they're not, then their alignment is deliberate. The math is telling. The estimated mass of the primary object was already troubling, larger than typical comets of its apparent brightness. But factoring in at least 5 additional bodies, some possibly denser, the total mass climbs sharply. This increase explains why orbital models started drifting weeks ago. It also means the cluster exerts more influence on its surroundings than initially calculated. Small gravitational influences propagate through the solar system like whispers, often invisible unless carefully measured. But here, the whispers are louder. The slight deflection in its trajectory already alters the predicted post-perihelion arc. If that arc changes further during the solar blind spot, tracking it afterward will be exponentially harder. Some mission planners are quietly running simulations on gravitational slingshot scenarios, not because they believe the objects are controlled, but because the geometry allows for the possibility of coordinated movement after conjunction. If the cluster shifts vector during the blind period, it could emerge on a completely different trajectory, while not foreseen in current ephemerides. There's another subtlety here. When these gravitational effects are modeled backwards, the cluster's earlier path seems too stable for a loose group of objects. Debris clouds wobble under tidal stresses. This formation does not. That stability suggests that the system either originated as a single massive body and fragmented in a highly symmetric way, which would be extraordinary, or has been maintaining formation for far longer than any natural debris swarm should. Inside certain research circles, this gravitational behavior is no longer a footnote. It's becoming the centerpiece. The idea that we may not be observing a single object, but a gravitationally bound system, is spreading fast. That distinction changes everything: how the encounter is modeled, how the risk is assessed, and what kind of event might unfold near the sun. The question isn't whether something is pulling, it's what kind of structure is holding it all together. Every major celestial event has a window in which it can be seen, measured, and understood. For 3I Atlas and its newly detected cluster, that window is closing. As the formation moves closer to solar conjunction, it enters a zone astronomers quietly call the blind corridor. A period when the sun's glare overwhelms optical instruments and line-of-sight tracking collapses. For objects near the ecliptic, this isn't just an inconvenience, it's a blackout. The blackout begins gradually. First, the faint signatures vanish. The smaller cluster echoes fade from ground-based telescopes, lost against the brightness of the inner heliosphere. Then, as the angle narrows, even the primary object slips beneath solar interference thresholds. By late October, most Earth-based observatories will be effectively blind. What happens next takes place in the dark. Historically, this blind corridor has hidden critical events. Cometary breakups, trajectory changes, sudden accelerations, all have occurred during solar conjunctions, only to be discovered days or weeks later when the object re-emerges. But 3 Atlas is different. It isn't a lone fragmenting body. It's a structured formation of multiple massive objects moving in apparent coordination. That means the blackout isn't just a gap in observation. It's a window of opportunity for change, for redirection, for something unexpected to unfold unseen. Mission planners refer to this interval with quiet unease. Space-based platforms like Solar and Heliospheric Observatory and Parker Solar Probe may catch partial glimpses, but their instruments weren't designed for tracking faint interstellar clusters with this kind of spacing precision. The solar background noise is immense. Even minor trajectory adjustments could go undetected. The concern isn't purely observational. When a formation enters solar conjunction, trajectory predictions become probabilistic rather than deterministic. The further into the blackout, the more the uncertainty grows. A small change in velocity undetected at perihelion can translate into millions of kilometers of deviation weeks later. It's not just a question of where it is, it's a question of whether post-conjunction models will still be valid at all. This uncertainty creates a tactical layer. If this cluster were purely natural, it would still present enormous analytical challenges. But if it behaves in a way that suggests internal structure or controlled dynamics, then solar conjunction becomes something else entirely, a shielded maneuver window. Hidden from our view, free from continuous tracking, the formation could alter its path without immediate detection. What alarms several analysts is the timing. The formation reaches maximum solar occultation precisely as the gravitational interactions between its components peak. This is when its dynamics are most likely to change. If a redirection occurs, we won't know until it emerges weeks later, possibly along a trajectory that diverges significantly from projections. In the language of orbital mechanics, this is the critical hinge point. Behind closed doors, certain observatories have begun preparing what they call shadow campaigns. These involve triangulating faint signals from deep space radio arrays, hoping to extract minimal data during conjunction. The odds of success are low, but not zero. A single anomalous ping, a fractional Doppler shift, a slight brightening near perihelion could provide the only clue to what happens in the blackout. What makes this particularly difficult is the lack of precedent. No interstellar object has ever entered conjunction with a known convoy of massive bodies moving in formation. When Oumuamua passed through, it did so alone. When 2I Borisov crossed, its trajectory was stable and predictable. But 3I Atlas carries complexity, a network of mass and motion that behaves more like a fleet than a fragment. The models strain under the weight of those variables. Observatories around the world are already adjusting their schedules. Some telescopes will pivot early, trying to collect final clear data in the last available observation window. Others are redirecting their focus towards secondary instruments, hoping for thermal signatures rather than optical confirmation. These are desperate, meticulous efforts to preserve a thread of visibility before the curtain falls. Meanwhile, agencies remain publicly silent. There are no official statements, no bulletins, no coordinated media briefings. That silence speaks volumes. When tracking uncertainty climbs above certain thresholds, public announcements often trail reality by weeks. By the time an official update reaches the public, the event may have already evolved into its next phase. What happens inside the observation gap isn't just unknown, it's unknowable, at least for now. The sun acts as both a shield and a veil. It blocks instruments, scrambles signals, and erases direct observation. And in that void, small anomalies can grow into decisive shifts. Some independent analysts have raised an uncomfortable possibility. If the formation is capable of controlled or semi-stable dynamics, the blackout may not be an obstacle for it, only for us. This is what turns a routine conjunction into a strategic inflection point. When the world stops looking, the story continues without witnesses. For months, orbital forecasts have shown a clean, predictable path after perihelion, a curve swinging back out into interstellar space. But those forecasts assumed a single mass, minimal forces, and no structural cohesion. Now, with a cluster in play, those forecasts may be little more than educated guesses. Even a slight alteration in vector during conjunction could mean the object doesn't follow the expected escape arc. It could linger, shift plane, or approach the ecliptic in ways no one planned for. There is one more layer beneath all this historical precedent. Conjunction blackout periods have hidden turning points before, sometimes benign, sometimes catastrophic. When Comet Encke made its close solar pass in the 19th century, it emerged fragmented, weaker, altered. When Comet Ison did the same, it disintegrated almost entirely during perihelion, but both were traditional comets, fragile under solar stress. This cluster is something different. It shows no tail, no visible sublimation, no expanding debris field. Its silence suggests resilience. That resilience creates a second problem. If the cluster maintains formation through perihelion, it won't just reappear. It may emerge stronger, more tightly locked, perhaps on a cleaner trajectory. That means less dispersion, sharper tracking, and a formation that behaves like a single coherent structure, a structure we will have no data on during its most critical maneuver window. Agencies know this. They've begun adjusting risk parameters in internal forecasts. Some observatories are extending funding to keep instruments trained on the region weeks after conjunction, anticipating surprises. Others are deploying fallback observation protocols, methods designed not for certainty, but for rapid reacquisition when the object reappears. The world will watch the horizon after the blackout, like waiting for a silhouette to re-emerge from blinding light. The interval between disappearance and reappearance may span weeks. In that silence, simulations will multiply and speculation will harden. Trajectories will diverge on paper long before they diverge in the sky. And when the cluster finally returns to view, it may no longer be where the models expect. The formation's orbit has never been clean. Even in the earliest observation runs, before the echoes appeared, analysts flagged small irregularities in its trajectory. They were brushed aside at the time, chalked up to imprecise readings from distant instruments. But once the cluster signatures were isolated, those early irregularities stopped looking like errors and started looking like fingerprints. Orbital solutions for interstellar objects typically follow predictable hyperbolic curves. Their paths are influenced by the sun's gravity, solar radiation pressure, and, if they're active, sublimation jets. 3 Atlas has defied that simplicity from the beginning. Its trajectory shows minute but persistent deviations that don't fit standard cometary outgassing patterns. And with the new objects factored in, something else emerges, a corridor. Instead of a natural scattering of debris, the cluster follows a narrow, coordinated channel through space. Their velocities are nearly identical, their spacing is measured, their lateral drift is almost non-existent. If these were naturally broken pieces, they should be diverging, fanning outward along their shared orbit. Instead, they're threading the same invisible needle as if bound to an orbital rail no one can see. The anomaly becomes sharper near perihelion. Models show that the cluster should be widening under solar pressure, but it isn't. The geometry remains tight. Solar radiation, which usually acts like a soft wind on a loose debris field, appears to have little effect. This implies unusual density, aerodynamic shaping, or active stabilization, all equally difficult to explain with natural mechanics. When analysts plot the orbital plane across multiple time intervals, something else surfaces: periodic micro-adjustments in velocity. These aren't random nudges from gas jets or solar tides. They're consistent, rhythmic, almost metronomic in their pacing. A subtle repeating pattern that gently keeps the objects aligned along their shared track. This rhythm shouldn't exist in nature, not like this. Most comets are chaotic near the sun. Even strong metallic-rich bodies show thermal irregularities. But 3 Atlas and its companions behave more like a stable array gliding on rails. Some scientists have started referring to it off-record as a fixed arc anomaly. The phrase hasn't appeared in any official bulletin, but it's circulating quietly in private channels and technical logs. If the orbital corridor holds through perihelion, something significant happens. The cluster will exit solar conjunction as a coherent structure, retaining its original alignment despite the most extreme gravitational gradient in its path. That would mean either an extraordinary coincidence of natural conditions or a behavior that suggests deliberate stability. Both scenarios are extraordinary for very different reasons. There's another layer hidden beneath this orbital neatness. The cluster's perihelion distance, the closest point to the Sun, is slightly lower than early estimates suggested. Not enough to trigger alarm in public channels, but enough to raise eyebrows among orbital dynamicists. It implies either a miscalculation in the original solution or a slight shift over time. That shift aligns almost perfectly with the moment the cluster's echoes became visible. What does that mean? If the cluster's effective center of mass changed, its perihelion would shift accordingly. But that only happens in three cases: active propulsion, fragmentation, or external gravitational influence. There's no evidence of outgassing jets, no sudden debris halo, and no obvious external body nearby, which leaves a void, a question without a neat answer. One scenario gaining quiet attention is gravitational shepherding. In celestial mechanics, smaller bodies can stabilize each other by exchanging angular momentum, like tiny dancers adjusting their steps to stay in formation. It's rare, delicate, and usually only observed in tightly bound systems like planetary rings or artificial satellite formations. Seeing something like this at interstellar scale near the Sun is virtually unheard of. Several research groups have attempted to model the cluster's motion using conventional celestial mechanics. None of the models fully replicate the stability. When random noise is added to the system, as it would naturally occur, the formation collapses. But in reality, it doesn't. It persists. That resilience suggests either some hidden stabilizing mechanism, gravitational or otherwise, or a factor no one has identified yet. The anomaly has also begun to affect mission planning. Organizations that rely on orbital prediction models to point telescopes or schedule space probe observations are quietly revising their forecasts. Some have expanded their error margins. Others have begun treating the cluster as a dynamic rather than passive target, a subtle but significant shift in operational thinking. In the realm of orbital dynamics, predictability is everything. When an object refuses to behave predictably, it forces the conversation into uncomfortable territory. The words controlled and coordinated don't appear in official briefings, but they linger in private discussions like static in the background. As perihelion approaches, every hour of clean data becomes critical. Observers are no longer just trying to track a trajectory, they're trying to understand what's holding it together. If the anomaly persists through the blackout, the story that emerges on the other side of the Sun may look nothing like the one we've been told so far. The corridor has been drawn. Something is following it with precision that defies natural expectation. And if that precision continues to hold, this event is no longer about a wandering visitor from deep space. It's about something far stranger. When 3I Atlas was first catalogued, its estimated mass was already pushing the edges of what astronomers expected for an interstellar body of its size and brightness. That estimate has now collapsed under the weight of new data. With the additional objects accounted for, the total system mass no longer resembles that of a wandering chunk of ice and rock. It looks like something orders of magnitude heavier, and that changes everything. The calculations began with photometric measurements. Normally, the brightness of a cometary object gives a rough idea of its size and density. But in this case, the luminosity was inconsistent with a single solid body. It was too high in some passes, too stable in others. At first, analysts thought it was surface reflectivity, an unusual albedo that could make a modest object appear larger. But then came the gravitational deviations. Those small shifts in trajectory measured earlier were critical. They allowed dynamicists to reverse engineer the effective gravitational mass of the cluster. The numbers were sobering. Instead of a single object with a mass comparable to a typical comet, the formation's combined gravitational influence suggested something tens, possibly hundreds of times more massive. This wasn't a single boulder gliding through the void. It was a gravitational system in its own right. The key anomaly lies in how the mass is distributed. Each object appears to have a comparable density, or at least the gravitational signature implies they're not hollow. And unlike icy comets, which lose mass as they approach the sun, these objects show no measurable loss at all. No tail, no jets, no dust halo. Their apparent masses remain stable across multiple observation cycles. That stability is not normal. Even metallic asteroids show surface activity under intense solar heating. But 3I Atlas and its companions remain inert, silent, cold in terms of emission behavior. They act like sealed objects, impervious to the usual forces that tear smaller bodies apart. If they're natural, they must be made of something extraordinarily dense. If they're not, then there's something else entirely. Another layer to this puzzle is the formation's center of gravity. When the gravitational effects are mapped across time, the entire cluster behaves as if bound to a single shared center of mass, slightly offset from the primary object. This is a crucial detail. If this were merely a swarm of fragments, each would pull individually, leading to chaotic dispersal. Instead, the pulls synchronize around a central gravitational anchor point, like beads orbiting an unseen core. This has led some researchers to quietly speculate about a hidden mass, something not directly visible on optical instruments, perhaps a large dark body acting as the gravitational spine of the entire formation. Others caution against such speculation, pointing out that dense metallic cores or unusually stable gravitational resonances could produce similar effects. But none of the natural scenarios fit neatly. What troubles analysts most is how the mass increase intersects with the timing of the solar blackout. A larger mass means stronger gravitational leverage. If the formation makes even a small maneuver, deliberate or natural, during conjunction, its post-perihelion trajectory could shift in ways that make it far harder to track or predict. The heavier it is, the more momentum it carries, and the longer that influence will persist across the inner solar system. There's also a structural problem. A system of this mass and density should have shown signs of internal interaction by now. Collisions, shedding, stress fractures. None of that has been observed. The spacing between the objects has remained stable, like components in a designed array rather than fragments drifting apart. This stability is held under gravitational forces that should have caused disruption weeks ago. Independent observatories have run their own numbers, and while they differ on specifics, they all converge on the same unsettling truth. The total effective mass of the formation is far beyond what was initially reported. Some estimates place it in the range of large metallic asteroids, others even higher. What they can't explain is why that mass hasn't betrayed itself through traditional cometary behavior. A few faint signals hint at something various. Deep space radar sweeps show unusually clean returns, too clean for a rubble pile. It's as if the surfaces are smooth, possibly reflective, or structured in ways not typical of natural rock. That doesn't prove anything, but it adds another quiet footnote to a growing list of unresolved questions. In celestial mechanics, mass dictates power. It shapes trajectories, bends light, alters probability curves. A system this massive moves differently, resists external forces differently, and can remain cohesive under conditions that would shatter ordinary debris fields. This is what makes the mass problem so central to the 3I Atlas mystery. The more precise the measurements become, the less it resembles what was expected. During the upcoming observation blackout, this mass won't just be a number on a chart. It will determine how much the system can pivot, how far it can drift, and how unpredictable the aftermath will be when it emerges from behind the sun. Analysts are preparing for trajectory projections to diverge significantly in early December once post-conjunction observations resume. The silence around this topic in official communications is telling. Agencies that were quick to label the object a harmless interstellar visitor months ago have gone quiet. Updates are delayed, bulletins are sparse. Even private research groups have tightened their communication channels. This kind of silence doesn't happen when an object behaves normally. The first thing that stood out wasn't what the cluster was emitting, it was what it wasn't. Normally, when an object of significant mass approaches perihelion, it begins to talk. In astronomical terms, it starts releasing energy into its surroundings. Comets produce gas and dust tails. Asteroids scatter faint thermal signatures. Even inert fragments show flickers of interaction with solar radiation. But as the 3I Atlas cluster approached the critical solar corridor, the instruments registered nothing. No jets, no tails, no spikes in radio backscatter, no flickering thermal rise. This silence isn't subtle, it's absolute. High-resolution spectrographic scans that would normally reveal sublimation trails came back flatlined. The absence of volatile emissions suggests either surfaces entirely sealed against solar heating or materials with melting and vaporization points far beyond what most comets can endure. In other words, this cluster isn't behaving like anything fragile. It's built to survive. Radar sweeps tell a similar story. When Goldstone Deep Space Communications Complex and other long-range instruments probed the region, they expected noisy, uneven reflections, the kind that signal a rough natural surface. Instead, they got clean, narrow-band returns. No scattering, no dispersion, no complex interference patterns, just sharp, consistent echoes that look more like metal than dust. Thermal infrared readings are equally strange. As the objects approach the sun, they should be heating unevenly, radiating out into space. But the detected signatures remain surprisingly uniform. That implies either extraordinary thermal inertia, as if the objects are made of a dense, conductive material that disperses heat rapidly, or some kind of reflective property that keeps solar energy from sinking in. Either explanation would make this cluster far more resilient than a standard interstellar body. This silent behavior is what's forcing analysts to re-evaluate their assumptions. If the objects were cometary, we would see signatures by now. If they were rubble piles, we'd expect to detect instability under thermal stress. Instead, the cluster has entered solar proximity with a kind of composure usually reserved for something built to withstand it. The silence doesn't just speak to composition, it affects tracking. Many traditional observation methods rely on sublimation activity to highlight the object against solar background noise encuentro. Without a tail, without gas jets, without any of the standard signatures, the cluster becomes exponentially harder to track as it approaches the sun. It's like watching a formation glide into a blinding storm without leaving a wake. Some analysts argue that this behavior could point to high-density metallic cores, similar to iron-nickel asteroids, but far more stable. Others push further, suggesting that this kind of silence may hint at controlled or engineered surfaces designed to minimize interaction with their environment. No one is saying that out loud in official reports, but in the quiet spaces of data-sharing networks, the word intentional is starting to appear more often. The lack of signals also introduces another problem: no clear indicators of stress. When comets approach perihelion, their internal structures crack and vent. Even if they survive, they usually leave traces of their passage. Spikes in brightness, sudden accelerations, gas signatures. This cluster, by contrast, seems immune. The tracking curves show no pre-perihelion twitch, no mass shedding, no instability. If anything, the formation appears steadier the closer it gets. One of the most intriguing details comes from passive radio sweeps. Instruments scanning wide bands around the formation picked up only solar background noise. Nothing distinct, no anomalous frequencies, no transient bursts. This doesn't prove that the cluster isn't emitting anything, only that if it is, it's either outside the range of our instruments or so weak and tightly directional that we're not in the beam. The silence is total, but it might also be strategic. In mission control centers across several agencies, this quiet is creating tension. Engineers and analysts rely on emissions to feed trajectory models, especially during conjunction blackouts. Without those signals, the blackout will be absolute. There won't even be a thermal or dust trail to reacquire. When the cluster disappears behind the sun, it will vanish like a blade sliding beneath water. Some research teams have begun experimenting with indirect detection methods, monitoring solar wind disruptions, micro fluctuations in particle streams, even faint changes in heliospheric magnetic fields. If the cluster interacts with its environment at all, these secondary effects might betray its position. So far, results are inconclusive. The contrast with past interstellar visitors is striking. When Oumuamua passed through, it surprised analysts with its acceleration, but still emitted subtle reflective signatures. Borisov, on the other hand, behaved more like a classic comet, shedding material freely. 3I Atlas sits in between, or perhaps outside the spectrum entirely, a massive, silent formation gliding towards solar perihelion without a trace. The implications ripple outward. If it remains silent throughout the blackout, reacquiring it on the other side of the sun will be an unprecedented challenge. The cluster could shift trajectory, fragment, merge, or simply vanish into a new arc. And no one would know until the instruments find it again, or fail to. And so the silence grows heavier with each passing hour. Not because it confirms anything, but because it leaves no trail to follow. An object that doesn't speak is harder to find. A cluster that doesn't reveal itself is harder to predict. And in astronomy, silence isn't absence. It's a choice the universe makes to withhold its evidence until the story is already moving without you. Timelines are supposed to anchor events in something solid. In orbital mechanics, they are the backbone of prediction: perihelion, conjunction, reemergence, outbound arc. But the moment the new cluster objects were factored into the model, those timelines began to slide, small adjustments at first, then larger. What had been a stable sequence of expected milestones is now a shifting architecture of possibilities. The most immediate change concerns the perihelion timing itself. Early projections based on 3 Atlas alone placed its closest approach to the sun in a narrow window late in October. But after the gravitational effects of the additional bodies were fully integrated, that window stretched wider, first by minutes, then hours, then days. It's not just a delay. It's a drift that grows as more data is processed. The formation is moving like a system, not a single point. Its mass distribution, orbital corridor, and internal spacing are all influencing how it curves through space. That drift has cascading effects. Tracking systems that rely on fixed, predictive models must now update their timelines continuously. Every time the cluster shifts, it alters the trajectory predictions for its re-emergence after solar conjunction. Each adjustment adds more uncertainty to what was already a blind interval. And that means the exact moment when the formation will reappear on the other side of the sun is no longer something anyone can guarantee. The blackout was already a strategic vulnerability. Now it's paired with an unstable clock. Mission planning is quietly unraveling behind the scenes. Observation campaigns were built around specific windows, the last tracking opportunities before conjunction and the first reacquisition attempts after. Telescopes, deep space antennae, and spacecraft schedules are all tied to those windows. If the formation arrives early or late, even by a modest margin, it could pass through the post-conjunction reacquisition zone unnoticed. A formation this silent doesn't leave obvious breadcrumbs. If it misses that window, it could effectively disappear for weeks or even months. This isn't the kind of drift we're used to with comets or asteroids. Normally, outgassing produces predictable accelerations as objects approach the sun. Even Oumuamua's subtle, non-gravitational acceleration followed a smooth curve that could be modeled with some effort. But here, the shifts are discontinuous, appearing in steps rather than curves. One night the models hold, the next they're out of sync. The cluster isn't just drifting, it's adjusting. The timing shifts began to accelerate around the same moment the cluster's echoes became more visible in infrared bands. That may not be coincidence. The gravitational rebalancing that occurs as objects move closer together or redistribute their positions within a formation can create measurable timing shifts without any external propulsion. If the cluster is internally dynamic, those movements could explain why the orbital clock no longer behaves like a fixed system. For planners, this is a nightmare scenario. Space agencies operate on tight precision. Tracking something that can shift its timeline autonomously means you're always responding to what already happened, not what's about to happen. It turns every prediction into a retrospective guess. There's another detail buried in the telemetry that worries dynamicists. The perihelion angle is changing as well, not dramatically, but enough to alter the re-emergence geometry. A slightly lower perihelion angle could mean the cluster reappears at a steeper trajectory relative to the ecliptic, emerging from the blackout in a position that doesn't line up cleanly with the early tracking corridor. That could throw off even the best coordinated reacquisition campaigns. This is where the discussion gets serious. When you lose both timing and angle precision, reacquisition becomes probabilistic rather than deterministic. Telescopes must sweep wide areas of sky, burning precious observation time with no guarantee of success. The cluster's lack of tail or outgassing means it won't shine brightly like a traditional comet. If it slips out of view in a low signal-to-noise zone, it could remain hidden for a very long time. The timing shifts are also rippling through other fields. Gravitational analysts are quietly recalculating potential energy transfers between the cluster and nearby bodies. A small delay in perihelion combined with a trajectory deviation could translate into a very different outbound arc. In certain scenarios, the cluster could leave the solar system along a clean, hyperbolic exit path. In others, it could settle into a much slower curve, possibly interacting with the inner solar system for far longer than expected. There's a quiet discomfort inside the data rooms. Timelines don't normally behave like this without a clear cause. With comets, the cause is heating and gas release. With asteroids, it's gravitational perturbation. With engineered spacecraft, it's deliberate course correction. No one is claiming the latter, not publicly. But in the absence of visible natural causes, the shift remains unexplained. Some have pointed out that a formation of high-mass objects moving in structured alignment could behave in unexpected ways during perihelion. The closer they get to the sun, the more the system amplifies small perturbations. If one body shifts slightly, the others adjust to maintain spacing. It's a ballet of gravitational give and take that could explain the timing drift without invoking anything unnatural. But even then, the precision remains extraordinary. A particularly troubling scenario was modeled 2 nights ago by a European observatory. If the cluster's perihelion is delayed beyond a critical threshold, the post-conjunction trajectory could intersect the orbital corridor of the inner planets at a different time than expected. It doesn't necessarily mean impact, but it does mean the geometry of potential close approaches changes, and with timing shifts come communication delays. Many observation networks coordinate internationally, timing their signals and sweeps to maximize coverage. If the formation's perihelion slips without early detection, those networks could miss their narrow reacquisition windows altogether. A silent formation that moves slightly faster or slower than expected becomes, for all practical purposes, invisible until it chooses, or happens, to pass through a new observation corridor. There's also the human element inside the control rooms. Data analysts are trained to trust their timelines. When the numbers slide, confidence erodes. And when confidence erodes, decisions slow. No one wants to commit resources to a position that may be wrong by the time the data is processed. The blackout already looms like a horizon they can't see past. Now the horizon is moving. All of this converges on one idea: the clock is no longer ours. Whatever governs this cluster, whether it's pure physics, an unusual gravitational structure, or something else entirely, has taken control of the timeline. And the world's instruments can only chase its shadow. That's why many agencies are quietly rewriting their contingency plans. They're not just preparing for a shift in location, they're preparing for a delayed or premature reappearance. Some even whisper about the possibility of not reacquiring the object at all. If that happens, 3I Atlas won't just be an interstellar anomaly, it will be a ghost. Every solar conjunction creates a moment when Earth's instruments go blind. For most objects, that blackout is a simple inconvenience, a few weeks of uncertainty before they re-emerge on the other side of the sun, usually right where the math said they would be. But with the 3 Atlas cluster, this window is beginning to feel less like an observational gap and more like a shielded stage. A place where something can happen unseen, a space between what we can measure and what we can only infer. The timing of this blackout is almost unnervingly clean. Just as the gravitational effects grow sharper and the perihelion timeline begins to drift, the cluster slips behind the sun, out of sight. No telescope on Earth will be able to maintain line of sight during the critical phase. Radio signals will be drowned out by solar noise. Optical instruments will be overwhelmed. Infrared arrays will lose contrast in the glare. For weeks, this formation will exist entirely in the dark. Invisible, not because it vanished, but because the sun is in the way. To astronomers, this is an analytical nightmare. To strategists, it's something more dangerous, a maneuver. The concept isn't new. Space agencies have long recognized that solar conjunctions create natural blind spots. Deep space missions often plan around them, delaying communications or changing trajectories during the period when Earth can't track them accurately. But this is the first time in modern history that an interstellar object, or rather an entire cluster of them, is moving into that window with such precision, silence, and mass. Here's the problem. If the cluster were a typical natural body, it would follow its expected trajectory through perihelion, emerge weeks later, and resume its outward path. But with the mass anomalies, the lack of outgassing, the stable formation geometry, and the timeline drift, no one can say with certainty what it will look like or where it will be when it reappears. That uncertainty is amplified by the fact that the blackout occurs precisely when the cluster reaches its point of maximum solar acceleration. If anything is going to change, that's when it will happen. Multiple agencies have quietly labeled this interval a strategic vulnerability, not because they know something is about to happen, but because they won't be able to prove if it does. A slight redirection, a reshaping of the formation, even a change in velocity could occur during conjunction without leaving a detectable trace. By the time it emerges again, it may be moving on a trajectory that the last pre-blackout models can't predict. The use of the term strategic is deliberate. This is not about speculation of alien intent, at least not officially. It's about the recognition that an object with unusual stability, high mass, and minimal emissions can make trajectory shifts that are nearly impossible to detect in real time. And that means no one can rule out sudden changes until they're already a fact. Inside certain research facilities, simulations have begun exploring what-if scenarios. One model assumes a slight increase in solar-assisted velocity, just enough to shave a few days off its re-emergence schedule. In that case, the object would appear ahead of every planned reacquisition window, slipping through the narrow band of telescope alignments before anyone notices. Another model explores the opposite, a deceleration during perihelion, delaying reappearance until well after most observation campaigns have expired. Both outcomes result in gaps, hours or even days, in which the cluster's position would be unknown, untrackable, unconfirmed. This silence of the object compounds the problem. Typical comets or asteroids leave behind thermal or dust signatures that can be picked up even through heavy solar interference. 3I Atlas emits nothing. It leaves no visible trail. It will vanish into the solar limb like a knife into black water. And when it reappears, it could be anywhere along a corridor far wider than the planned observation arcs. This is why some analysts refer to this as a window of maneuver. If something wanted to disappear or simply act without being observed, this is where it would happen. The geometry, the timing, and the behavior of the formation align perfectly with the kind of uncertainty that makes tracking almost impossible. None of this means there's intent. It may all be coincidence, the inevitable convergence of celestial mechanics and bad timing. But even without intent, the strategic implications remain the same. An object that no one can observe can change in ways no one can anticipate. By the time it returns to view, the story may have already shifted. This isn't just a scientific problem, it's also a communications problem. Agencies around the world coordinate their public statements around predictable events. They like clean narratives. The object will vanish on this date and reappear on this date. But behind closed doors, they know that they can't guarantee those dates anymore. The timeline has shifted too many times. The models have grown too unstable. That uncertainty forces a kind of operational silence. If they announce a precise date and the object doesn't appear, it invites panic. If they announce nothing, they risk losing public trust. So for now, most remain quiet. Quiet is safer than wrong. Meanwhile, observation teams are preparing for the possibility that when the cluster does emerge, it won't look the same. If the objects change their spacing during perihelion, whether by internal adjustment or external forces, the formation could reappear as a different structure entirely, tighter, looser, fragmented, or something more organized. The phrase coordinated geometry has begun to appear in technical bulletins. It's not sensational, it's cautious. A structured formation that survives perihelion intact is not something easily dismissed as coincidence. The solar environment is unforgiving. If it endures unchanged, it suggests a degree of internal cohesion that no previously observed natural object has exhibited at this scale. And then there's the elephant in the room, one that no agency wants to address directly. If the formation re-emerges on a significantly different trajectory, there may be no way to know whether that change was the result of natural forces or something else. Solar pressure, gravitational interactions, or an intentional maneuver would all look identical from our vantage point during blackout. The sun erases the evidence. The last tracking opportunities before conjunction are already underway. Every night, observatories squeeze the final drops of data out of the fading object before the sun swallows it whole. Those data points will define the search patterns for weeks to come. If the object veers off course after that moment, everything downstream becomes guesswork. Strategists describe this window as opaque space, a theater where reality continues, but our ability to perceive it ends. Historically, opaque space has hidden comets breaking apart, asteroids shifting trajectories, and probes changing velocity. Now it will hide something far stranger, a massive, silent, coordinated formation from outside the solar system. What happens inside that window will set the tone for everything that follows. If it reappears where expected, this remains a strange but measurable event. If it doesn't, the narrative breaks. The object becomes a variable that no model can contain. For months, the world has been looking at 3 Atlas as a mystery to be solved. But during this brief, shielded moment behind the sun, the mystery belongs to it alone. Every interstellar object that passes close to the sun changes in some way, whether through sublimation, fragmentation, or gravitational slingshot. None leave perihelion untouched. For 3I Atlas and its silent convoy, this rule carries a much heavier weight. Its mass, formation, geometry, and timing make the post-perihelion phase more than just a continuation of its journey. It's the moment when its trajectory can be rewritten entirely. The possibility of redirection isn't a sensational theory, it's simple orbital mechanics. When an object approaches perihelion, even small changes in velocity can produce massive deviations on the other side of the sun. This is how spacecraft use gravity assist to change direction without expending fuel. A precise nudge at the right moment can shift a trajectory by millions of kilos downrange, and this formation is entering the most efficient gravitational corridor it will ever experience inside our solar system. What makes this dangerous is the silence. Natural objects usually announce these changes through visible cues. Comets brighten, fragment, accelerate, asteroids heat up, flare, sometimes break apart. Even tiny fragments leave trails that help analysts detect course shifts early. But the 3 Atlas cluster gives no warning. If any redirection occurs during conjunction, no one will know until it emerges. And by then, it may already be too late to predict where it's heading. This possibility isn't hypothetical anymore. Small, unexplained velocity shifts have already been measured in the weeks leading up to the blackout. Nothing explosive, nothing chaotic, just slight deviations that stack quietly like pressure behind a dam. If that pattern continues unseen during perihelion, the outbound path could diverge sharply from the last recorded arc. Several space agencies have already run simulations using 3 scenarios: passive drift, gravitational assist redirection, and powered maneuver. The passive scenario assumes the object simply continues on its curved hyperbolic escape path. That's the safest option, and also the least likely to explain the pre-blackout timeline drift. The gravitational assist scenario is more complicated. If the cluster shifts velocity naturally during perihelion, even by a fraction of a percent, the resulting arc could bend toward a slower outbound trajectory, intersecting the plane of the inner solar system. That wouldn't imply intent. It's something many comets experience, but it would make future encounters far more difficult to predict. It would also extend the observation campaign for years. The third scenario is the one no one wants to discuss openly. If the formation undergoes a deliberate redirection during blackout, it could emerge on a vector outside the expected search corridor entirely, and because it doesn't emit detectable signals, it could remain invisible for a long time afterward. A massive silent object that can redirect undetected is not just an astronomical anomaly, it's a blind spot. The danger isn't that the object will collide with Earth. Statistically, the odds of a direct impact are vanishingly small. The danger lies in losing track of something this large. An object of this mass could have downstream gravitational effects on other bodies. interfere with long-term orbital models, or simply vanish into the dark, reappearing years later in a completely different sector of the solar system. In practical terms, it would be a ghost. The timing of perihelion amplifies the risk. Solar conjunction is the most turbulent part of its orbit. Even minor gravitational interactions between the cluster's individual components can trigger shifts. A slight rebalancing of its internal structure, say two objects drawing slightly closer together, could alter the system as center of mass. That alone might be enough to bend its outbound path. No engines required, just precision and timing. Some analysts have speculated about the formation acting like a gravitational sail. If the objects are dense and arranged in a specific configuration, they could exploit the sun's pull and their own momentum to steer themselves slightly, not unlike how spacecraft perform low-thrust adjustments over long distances. It wouldn't take much. A few millimeters in delta V at perihelion could produce millions of kilometers of divergence months later. If that happens, every reacquisition campaign after conjunction becomes a search rather than a confirmation. Telescopes would need to comb through a vast area of space with no guarantee of success. And since the formation emits nothing, no tail, no radio, no thermal plume, it could slip through those nets unnoticed. This is why several agencies are quietly recalculating their fallback strategies. They're considering the possibility that the object won't appear where predicted. In those scenarios, they'll shift from direct reacquisition to deep sky sweeps, focusing on gravitational influence rather than light. Instead of looking for the object itself, they'll look for how it bends the space around it. That's not easy. Detecting gravitational signatures without direct observation requires high precision over long periods. It's the kind of monitoring usually reserved for exoplanet searches or dark matter mapping. Using it on something inside our solar system speaks to how seriously the redirection scenario is being treated. There's also a deeper unease, one that doesn't appear in official bulletins, but is quietly acknowledged in private discussions. If the object redirects during conjunction, we will never know how or why. The sun erases the evidence. By the time it reappears, the change will already be history. This creates what some strategists are calling the silent interval. It's not just that the object is hidden, it's that decisions can be made, whether by nature or something else, during that period that determine its future trajectory without any observational record. That silence is total. It's not a blank space to be filled. It's an absence that can never be recovered. Even without speculation, the facts alone are unsettling. A multi-object high-mass cluster entering solar conjunction with measurable velocity shifts. A blackout window at the exact moment when those shifts would matter most. A history of silence that offers no clues to what it might do next. This is why the term redirection risk isn't a headline. It's an operational phrase. It appears in planning documents, internal briefings, even classified channels. It's not about predicting what will happen. It's about acknowledging that for the first time, we're dealing with something that can change its course during a period in which no one can watch. For the scientific community, this is a problem of physics and uncertainty. For the people tasked with tracking near-Earth objects, it's a problem of control. The sky is supposed to be predictable. When it isn't, everything downstream starts to shift. Whenever an event like this begins to gather momentum, especially one surrounded by silence, missing data, and shifting timelines, the world splits into two camps. One sees coordinated movement, hidden dynamics, or even deliberate redirection. The other sees what it always sees: physics, ordinary, explainable, if complicated celestial mechanics. The counter-arguments to the more alarming interpretations of the 3 Atlas cluster are already taking shape inside academic papers, private correspondence, and quiet briefings. The first counter-argument is the most obvious. fragmentation physics. Objects that pass close to the Sun sometimes fragment in symmetrical ways. If a single body splits cleanly, its fragments can maintain close spacing for weeks or months, particularly if they're dense and moving along nearly identical vectors. Under this model, what looks like a structured convoy may be nothing more than a lucky or unlucky break, a fracture event that just happened to produce an unusually stable formation. Supporters of this view point to past examples like Comet Shoemaker-Levy 9, whose fragments entered Jupiter's gravity well in a stunningly ordered train. That was a natural event, not a controlled one. They argue that symmetry doesn't necessarily imply design. It can arise from the way a body rotates before it breaks, or how the Sun's gravity pulls at a fractured core. The second counter-argument focuses on high-density composition. If the objects are made of dense refractory material, iron, nickel, or even something more exotic, they would behave very differently from comets. They wouldn't outgas. They wouldn't produce tails. They'd remain dark and silent, absorbing or reflecting light in unpredictable ways. This could explain the lack of emission signatures without requiring anything unnatural. We've never tracked an interstellar object of that size and density before. It could simply be behaving like one. Under this interpretation, the cluster's behavior near perihelion would mirror the quiet grace of a strong, unyielding object resisting solar stress. The mass anomalies might be less mysterious than they seem, a series of dense metallic fragments moving together after a clean break, forming a compact gravitational ballet that, while rare, is not impossible. A third line of reasoning emphasizes observational bias. Solar conjunction is a data vacuum, and vacuums amplify mystery. Because we can't observe the object continuously, we fill the silence with projections, guesses, and possibilities. Some of those possibilities sound extraordinary, but they might not be necessary at all. Many comets and asteroids have behaved strangely near perihelion simply because the observations were incomplete. When they finally reappeared, their trajectories made sense in retrospect. Skeptics argue that the timeline drift might be less dramatic than it seems. It could be an artifact of noise in the data, small errors that stack as analysts try to model something without complete information. A blackout gap means uncertainty grows exponentially. What looks like hidden intent might just be poor resolution. There's also the solar pressure argument. Some dynamicists believe that what appears to be controlled formation flight could actually be a natural equilibrium caused by differential heating and reflective forces. If each body has similar reflectivity, shape, and mass, they could settle into a synchronized drift held together not by engines or intent, but by subtle forces acting uniformly. This would be rare, but not unprecedented in celestial mechanics. Even the redirection risk, the most unsettling aspect of the scenario, has a natural explanation. Objects often undergo minor orbital shifts during perihelion because of unmodeled factors. Asymmetric heating, microfragmentation, gravitational interactions with their own debris fields. Most of these shifts aren't detected until the object reappears. When Oumuamua accelerated slightly on its way out of the solar system, the lack of immediate explanation spawned speculation. But later, most researchers settled on natural, if complex, explanations involving outgassing we simply couldn't detect at the time. There's another layer to these counter-arguments, the psychology of anomaly. When events occur in partial darkness, the mind builds bridges over the gaps. History is full of astronomical mysteries that seemed impossible in the moment, but later resolved into natural phenomena once better instruments became available. Skeptics argue that 3 Atlas is no different, just another interstellar oddity magnified by timing, media interest, and a solar blackout at the worst possible moment. Some scientists also point out that the cluster's stability might not last through perihelion. While its geometry has held impressively so far, the Sun is unforgiving. Thermal gradients, gravitational tides, and small collisions could easily disrupt the formation. By the time it reappears, they argue, we may find nothing extraordinary, just a handful of scattered fragments on diverging trajectories, indistinguishable from the aftermath of a natural break. Agencies are quietly divided. Some internal teams lean heavily toward these natural explanations, seeing nothing more than a particularly stable fragment cluster entering a standard gravitational slingshot. Others are more cautious, unwilling to dismiss the precision, timing, and silence as mere coincidence. But everyone agrees on one thing. Until the object re-emerges from behind the Sun, the debate is academic. Still, these counter-arguments serve a critical purpose. They keep the narrative grounded in physics, forcing every extraordinary claim to compete with simpler, testable explanations. The notion of a maneuvering interstellar cluster may sound dramatic, but it must still outcompete the far more likely possibility of complex but natural orbital behavior. When the world looks back on this event, days, weeks, or even years from now, it may remember this as the moment we saw patterns in darkness and mistook them for intent. Or it may remember it as the first sign of something stranger moving through the inner solar system. Either way, the skeptics are right about one thing: the data will decide. And for now, the data is locked behind the Sun. Every astronomical event has two stories. The first is what the data tells us. The second is what happens when the data stops. Right now, the second story has begun. For 3 Atlas and its silent formation, the last confirmed observations are already fading into history. The ground-based telescopes that once tracked its faint echoes have either gone dark or turned away. Solar interference has swallowed the final signals. The radio noise from the Sun overwhelms every listening array on Earth. In effect, the cluster has stepped off the visible map. This is the period analysts call total silence. It's not just an absence of telemetry, it's the suspension of certainty itself. In every previous phase, even during timeline shifts and mass anomalies, there was still data, imperfect, noisy, fragmentary, but data nonetheless. Now, for the first time since the formation was identified, there is nothing. This silence is a familiar but unnerving part of solar conjunction. Probes, comets, asteroids, they all pass through it. But never before has an interstellar object of this complexity and mass entered the blackout with so many unanswered questions attached. This isn't just the silence of the unknown. It's the silence of a situation already stretched thin by anomalies. Inside mission control centers, screens that once streamed coordinates now show static. Automated tracking systems have been placed on standby. Observatories have shifted to a hold pattern, conserving resources for the re-emergence window. In this kind of quiet, even the absence of evidence can feel like a statement. Teams are not entirely idle, of course. What happens during the blackout is less about watching and more about anticipating. Simulations continue to run around the clock. Analysts input every final piece of pre-blackout data into trajectory models, creating thousands of branching possibilities for what might happen on the other side of the Sun. These simulations diverge quickly, like cracks spreading through glass. Within just a few days, the uncertainty corridor balloons from a narrow band to a vast fan of possibilities. The object could emerge slightly early or late. It could appear in its previous formation or fragmented. It could follow its original trajectory, or it could bend sharply away from it. All of these outcomes are mathematically plausible, and none can be verified until the cluster returns to view. Some teams are trying a more indirect approach. Since direct observation is impossible, they're attempting to listen for what isn't the object itself, but its effect. Solar wind monitors are being used to look for micro disturbances in the heliosphere. High sensitivity detectors scan for changes in solar particle flow that might hint at the passage of massive objects. So far, nothing conclusive has surfaced. The sun is too loud. Others have turned to deep space radar and gravitational perturbation monitoring. If the cluster's mass is as significant as the calculations suggest, it may produce subtle ripples in nearby objects' orbits, many gravitational fingerprints left in the inner solar system. But these signals, if they exist, are buried deep beneath layers of noise and would take weeks to isolate. And so the silence stretches. This is the moment when speculation tends to overtake science. History is full of precedents. When Comet Ison passed behind the Sun in 2013, observers didn't know whether it would survive. Rumors filled the void. Some said it had disintegrated, others claimed it had changed course. Only when it emerged did reality overwrite the speculation. Something similar happened with Oumuamua. A single, unexplained acceleration led to a flurry of theories before better models arrived. But there's a key difference here. Those objects made noise. They left thermal signatures, reflective spikes, or visible tails. The 3I Atlas cluster does none of that. Its silence is sharper, deeper, more complete. It leaves no trail, no thermal wake, no natural flare to follow through the glare. This means the first reacquisition signal after conjunction won't just be important. It will define the narrative. If the cluster reappears where predicted, many of the stranger hypotheses will collapse overnight. If it doesn't, the narrative will fracture further. Either way, that first detection will carry more weight than weeks of speculation. In some corners of the astronomical community, this silence is being treated like an experiment, not by choice, but by necessity. How a system like this behaves during total observational blackout will teach scientists as much as any telescope image could. If it emerges unchanged, the stability of its geometry will set a new precedent for interstellar objects. If it doesn't, then the deviation will expose forces that weren't previously accounted for. But there's a deeper tension beneath the analytical calm. It's the awareness that this isn't a routine object, and this isn't a routine silence. The mass, the pattern, the timing, all of it combines to make the blackout feel less like a pause and more like a chapter being written where no one can see it. This is why so many observatories are preparing their instruments in advance, days before the projected re-emergence. The moment the sun's glare fades enough to see past the limb, they'll be ready. Telescopes are already aligned. Algorithms are primed to sweep the search corridor. Every piece of hardware capable of detecting faint, fast-moving objects will be listening, because the cluster's silence is a double-edged blade. It makes it invisible, but it also means the first hint of its return could come without warning. A faint signal on a radar sweep, a slight thermal uptick in an infrared scan, a soft, unnatural echo in the solar wind. One single data point could pull the object back out of the void, or nothing might come at all. That possibility, the one where nothing returns, is rarely discussed aloud. Officially, every agency assumes reacquisition. But in private, some analysts are preparing for the alternative, a scenario where the cluster simply doesn't appear where expected or at all. In that case, the mystery of 3 Atlas won't end with answers. It will expand outward into the dark. When the blackout began, the models scattered like dust. But something subtle was hiding inside those branching trajectories. As teams pushed their simulations forward, factoring in the gravitational mass and the measured pre-conjunction velocity shifts, a strange coherence began to emerge. Most of the trajectories, even when starting from slightly different inputs, converge toward a narrow range of motion, not random, not chaotic, coordinated. Coordinated motion in celestial mechanics is a rare but not impossible phenomenon. Moons locked in orbital resonance can move this way. Tightly bound clusters of dense asteroids can do it for short periods. But here the precision is sharper than expected. These objects, supposedly fragments or natural debris, appear to be holding spacing and relative velocity across a high-stress orbital event. That alone would make this one of the most stable interstellar formations ever recorded. The evidence starts with the velocity fields. Just before solar conjunction, the leading and trailing objects in the cluster displayed symmetrical drift patterns relative to the primary body. That's crucial. Normally, solar acceleration would create differential spacing as the objects respond differently to solar pressure. Instead, they adjusted together, as though responding to a shared center of mass. Even in the last visible frames, their spacing remained almost unnervingly uniform. Post-blackout projections sharpen this into something else. In the most likely trajectories, the formation maintains a constant ratio of spacing as it rounds perihelion. That ratio doesn't appear to be dictated by chance or weak cohesion. It looks deliberate, a configuration behaving like a flock, not a spray of fragments. Several astrophysicists have drawn parallels to the phenomenon of Lagrangian swarms, in which multiple bodies can maintain relative positions around a shared gravitational point. But what's being modeled here is far more structured. Instead of orbiting a point, the objects appear to be maintaining an aligned corridor through the inner heliosphere, a straightened path with minimal deviation. That corridor looks eerily similar to the filamentary structure mapped earlier in the year before the cluster was fully resolved. The word formation is beginning to circulate more freely in private technical discussions, not because anyone's ready to leap to conclusions, but because the behavior fits no other existing category neatly. Fragment clouds disperse. Binary systems wobble. Synchronous formations like this, stable through perihelion, are vanishingly rare in nature. The behavior of the lead object is particularly telling. In the final pre-conjunction velocity maps, it displayed slight deceleration, allowing the trailing bodies to close the gap. This kind of uniform tightening would be expected in a controlled convoy or in objects sharing a stable resonant mode. What it wouldn't match is chaotic debris behavior. If anything, the perihelion phase should have exaggerated differences, not dampened them. The internal modeling teams have started to talk quietly about vector discipline. That's a term usually reserved for spacecraft formation flight. It means every element in a group moves as if tethered by invisible geometry, adjusting in micro increments to maintain shape under stress. The models don't prove that's happening here, but they keep nudging in that direction. This is where the scientific community begins to fracture further. Skeptics argue that gravitational resonance between similarly dense fragments can mimic this behavior for short periods. They point to stable train formations seen in some asteroid clusters, but others counter that those formations occur in stable, low-energy environments, not during a near-solar pass under intense gravitational gradients. The timing is crucial. If the cluster emerges from conjunction with this spacing intact, it will mark the first time such coherence has been observed under these conditions. It would imply that the formation either possesses internal cohesion far beyond normal fragment swarms, or that it's behaving like a single system composed of multiple components. Neither interpretation fits comfortably into the textbook categories astronomers use. Agencies monitoring the event are already preparing for high-speed reacquisition. Tracking arrays are scheduled to sweep the expected corridor in layers, looking for not just one object, but multiple points moving in exact formation. A simultaneous detection across several points would confirm coordinated motion beyond doubt. That would not only rewrite the narrative, it would force a reclassification of the entire object. What's quietly unsettling analysts isn't just the alignment itself, but its precision at scale. The distances between the cluster's components are measured in tens to hundreds of kilometers, not millions. Yet they seem to be maintaining that spacing with minimal drift, despite approaching one of the most turbulent regions in the solar system. In purely physical terms, that means one of two things must be true. Either these objects are connected through an extraordinarily stable gravitational configuration that we've never seen before at this scale, or something is actively managing their relative positions. No one is saying that last part publicly, but behind the scenes, in secure channels and technical briefings, the phrase non-random spacing stability has become a point of intense debate. Engineers use words like rigid patterning and formation persistence. Astronomers use resonant stability. Strategists use something simpler: they're moving together. This is also where redirection risk deepens. A convoy-like formation is far more maneuverable, even through purely gravitational effects, than a single rigid object. A slight collective shift could alter not just the outbound vector, but its entire post-perihelion dispersion pattern. That would make reacquisition and future tracking exponentially more complex. Meanwhile, deep space radar stations are on alert. If the formation holds shape as it re-emerges, the radar echoes could reveal a geometric structure, not necessarily engineered, but structured in a way that distinguishes it from a random fragment swarm. The echoes themselves might align in patterns, and patterns in the context of celestial events are never ignored. Every hour that passes brings the first possible post-conjunction observation closer. Telescopes along the night arc of multiple continents are already aligned, waiting for the faintest flicker on the limb. If the formation emerges on schedule and in shape, it won't just confirm coordinated motion. It will confirm that something about this object is fundamentally unlike anything previously tracked in the modern era of astronomy. The first returning signal will decide how this story is told, either a chaotic scattering that fits the skeptic models, or a clean, unwavering pattern that forces a new vocabulary. Either way, the silence will break. And when it does, the shape that comes out from behind the sun will matter as much as its position. If the Three-Eye Atlas formation maintains its shape through perihelion, the implications won't stop with its reappearance. This is the chapter where trajectories stop being theoretical curves and begin intersecting with the architecture of the inner solar system. Even the smallest deviation in outbound vector during blackout can project into months or years of downstream effects. This isn't about a single observation. It's about the path it carves through everything that comes next. The first and most immediate consequence is orbital intersection. Even without direct maneuvering, gravitational slingshot effects from the sun are capable of bending the formation's trajectory sharply depending on the perihelion angle. Pre-blackout projections already hinted at minor timeline drifts. If those shifts compounded behind the sun, the outbound path could now cut through the orbital corridors of several inner planets. That doesn't imply a collision course, but it places the object in zones of heightened gravitational influence, where future perturbations become more complex and harder to model. In one scenario, the most conservative, the cluster swings out and exits the solar system on a clean, hyperbolic path. It leaves behind no more than a few questions and years of archived data for researchers to study. But other scenarios, already mapped in quiet simulation rooms, are less simple. If its outbound curve drags along the ecliptic plane instead of lifting away from it, it could linger, passing through regions populated by planetary bodies, satellites, and debris fields. That kind of lingering would make the object a permanent factor in solar system tracking models. Even if it never approaches Earth directly, its mass alone, distributed across several coordinated bodies, would require long-term monitoring, similar to how astronomers track major asteroids and comets with extended return periods. But unlike a normal asteroid, this formation would be harder to track and model because it doesn't behave like a rock. It moves like a structure. The mass factor amplifies everything. A single body of this size would exert modest but noticeable gravitational perturbations on smaller objects it passes. A formation of multiple massive objects could create complex, overlapping gravitational wakes. These wakes don't always appear in dramatic ways. Sometimes they manifest as small-term deviations in the orbits of other bodies, deviations that might not be noticed for years until they accumulate. Analysts in several mission planning divisions are already running shadow corridor models. These models don't predict a direct event. They map what-if zones, regions of space where the formation's gravitational influence could subtly interact with other trajectories. These zones intersect with orbital paths of inner system objects, including satellites, probes, and future-planned missions. If the cluster deviates even slightly from its expected path, those zones widen dramatically. This leads to the second major consequence: tracking strain. Interstellar objects are already notoriously difficult to monitor once they pass perihelion and start moving outbound. Their fading brightness, unpredictable light curves, and distance make follow-up observations progressively more resource-intensive. If this formation maintains its coordinated spacing, each component must be tracked individually, not as a single mass. That multiplies the monitoring effort exponentially. In other words, this object isn't just one trajectory, it's many moving together. The possibility of fragmentation during outbound flight complicates things further. If the formation fragments after perihelion, whether naturally or through stress accumulated during the solar pass, the resulting pieces could scatter along nearly parallel vectors. That kind of dispersion would look less like a singular event and more like a slow bleed of mass across multiple trajectories. For agencies tasked with tracking near-Earth objects, that's a logistical nightmare. Then there's the uncomfortable scenario, the one most public statements avoid: low-angle return corridors. If the trajectory flattens along the ecliptic even slightly, the formation could remain in the plane of the planets long enough for future close approaches. Not this year, not next year, but years down the line when its orbit crosses another object's path at the wrong moment. This isn't fear-mongering, it's math. The Sun is a natural accelerator, and perihelion is where trajectories are either flung outward or bent inward just enough to hang around. Most comets that survive their first close pass return centuries later. But a heavy, stable, non-fragmenting formation like this could move in ways that don't match those familiar patterns. Strategists inside major observatories have begun using language rarely seen in scientific contexts: trajectory opacity. It refers to the degree of uncertainty that grows over time when an object doesn't behave according to classical models. With normal comets, opacity fades as more data is collected. With silent formations like 3I Atlas, opacity grows because the lack of emissions or light makes reacquisition harder with each passing month. If the object remains unilluminated, the next chance to reacquire it may depend less on optical telescopes and more on gravitational tracking. That means monitoring how other objects, spacecraft, asteroids, even planetary orbits, respond to its presence. That kind of indirect detection is resource-heavy and imprecise. It would turn 3 Atlas from an observed phenomenon into a long-term background uncertainty. And then there's the psychological ripple, something scientists don't often account for, but strategists do. A silent, coordinated, high-mass formation that disappears behind the Sun and re-emerges on a new trajectory is the kind of event that does not stay confined to research papers. Once its outbound path becomes clear, the world will pay attention. Even small deviations from predicted arcs will fuel speculation. Political, scientific, conspiratorial. It will change how people talk about interstellar visitors, possibly for decades. The situation is especially sensitive because of the precision factor. If the formation emerges with its geometry intact, its outbound path will look less like a natural comet and more like something that obeys internal constraints. Natural or not, that perception will stick. Agencies are preparing for multiple reappearance narratives. In the best-case scenario, the cluster emerges exactly where expected. Its outbound arc matches the most conservative predictions, and the story becomes a technical curiosity for specialists. In the intermediate scenario, it reappears with slight deviations and lingering uncertainties, prompting years of follow-up studies. In the worst-case scenario, it reappears on a significantly altered trajectory, possibly flatter, possibly closer, and possibly harder to reacquire over time. That would shift the entire conversation from mysterious visitor to active long-term presence. That's what consequence path really means. Not drama, not sensationalism, just quiet, slow ripples of celestial mechanics expanding outward from one hidden moment behind the sun. The consequences won't appear as headlines overnight. They'll unfold in calculations, updates, minor orbital adjustments, and brief technical bulletins over months, years, maybe decades. The story of 3I Atlas doesn't end when it re-emerges. That's when the real story begins, the story of what path it chooses and how long it remains part of our sky. At some point in the days ahead, when the sun begins to tilt just enough for the glare to ease, the first observatories will begin to look again. They'll start with faint sweeps along the predicted corridor, a line of coordinates drawn from the last solid data before the blackout. Nothing about this process will feel dramatic. It will begin with silence, with empty frames, with sensors registering background noise, and then, perhaps suddenly, a flicker. That flicker, if it comes, will mark next contact, not in the communicative sense, but in the literal sense, a re-establishment of connection between our instruments and the object that has for weeks existed only as a mathematical ghost. The search has already been divided into tiers. The first tier belongs to ground-based telescopes along the Dawn Belt, Chile, the Canary Islands, South Africa, the only regions positioned to peer close to the sun's limb at the right angle. The second tier is orbital, with arrays like the Parker Solar Probe and SOHO expected to deliver their first overlapping data packets once solar noise diminishes enough to distinguish faint motion. The third tier will come from deep space radar systems sweeping the expected re-emergence zone. They won't see shape or texture. They'll see echoes, minute pulses bouncing off whatever passes through the coordinates they've been told to watch. Inside those first hours, tension will mount quietly. Analysts know that what they see, or fail to see, will decide which version of this story becomes history. If the cluster reappears intact, moving exactly as predicted, this will be classified as an anomaly resolved, a natural but rare gravitational ballet that simply tested the limits of current modeling. If it doesn't, if the spacing or position deviates too far, the implications multiply. The first frames will be studied pixel by pixel. Background noise will be stripped, contrast adjusted, every faint point of light scrutinized. This is where things get delicate. The 3I Atlas cluster isn't expected to shine brightly even after perihelion. Its surfaces don't emit or reflect in ways that make detection easy. That means reacquisition may depend on luck, a momentary break in solar interference, a brief flare from reflected sunlight, a single radar ping landing at the right instant. But beyond the purely technical challenge, the human dimension is already forming. In research labs across continents, teams that have spent months tracking, arguing, theorizing, are now united by the same quiet question: will it still be there? If the cluster appears unchanged, same geometry, same formation, it will become the most stable multi-body interstellar system ever recorded. Its endurance through perihelion would defy standard thermodynamic predictions. It would suggest internal cohesion or resonance mechanisms that go beyond anything documented. Papers will follow, debates will flare, and the term three-class object will likely enter scientific vocabulary as a new category. If, on the other hand, it reappears changed, the narrative fractures again. A tighter spacing could imply contraction or controlled repositioning. A looser one might signal post-perihelion drift. A missing body could mean fragmentation or something else entirely. Each variation will carry different implications, and each will be studied obsessively. And then there is the possibility, remote but not impossible, that nothing reappears at all, that the cluster has either broken apart completely or shifted beyond the reacquisition corridor. In that case, the story moves from science into mythology. The object would join the short list of cosmic visitors that vanished without closure, their final trajectories swallowed by the sun. The math would remain, but the evidence would be gone. Quiet contingency plans are already in place for each outcome. If reacquisition occurs, tracking networks will hand off data in real time across hemispheres using shared channels to refine orbital solutions hour by hour. If the formation fails to appear, the next phase begins automatically. Deep space surveys widening the search field, looking for gravitational anomalies when none should exist. Either way, every instrument pointed at the sky during those days will, in some indirect way, be looking for the same thing. Confirmation that the universe still obeys its own rules. The public may never know how close some of these data handoffs will come to panic. Inside the control rooms, however, the mood will not be fear, but something quieter, respect, the sense that a mystery, however it ends, has forced a recalibration of what is possible in celestial mechanics. No one knows what next contact will look like. It could arrive as a faint dot, perfectly aligned with the predicted coordinates, a triumph of persistence and physics. Or it could appear offset by a fraction of a degree, silent and intact, hinting that something behind the sun did in fact change. Or it may not appear at all, leaving behind only a void that will be filled with projections for years to come. Whatever happens, the event will close the observational arc of this first passage. But it won't close the story. If the cluster re-emerges, it will begin an outbound journey, one that could stretch across decades, perhaps centuries, before it vanishes back into interstellar darkness. Humanity will keep its coordinates archived, its light curves stored, its peculiar silence preserved in databases that future generations may reopen long after this one forgets.